Howdy! Welcome to Aspire Mountain Academy. I am Professor Curtis, your instructor for this course in Introductory Statistics. In less than 10 minutes, this video demonstrates how to make predictions with linear regression models. Let's get started. So, all this stuff that we're talking about with linear regression is not so that we can look cute. The real power of regression lies in the ability to predict one variable given the other. And the predictive ability of your model can be so accurate, okay? If you get it right, you get some good data and you get it right, the prediction of abilities of these regression equations are just out of this world, amazing. And this is the real power of statistics, that you can actually not just describe characteristics of a population given a sample, but you can take a sample and use it to make predictions about where the population is going to be tomorrow. That's absolutely out of this world amazing. Of course, that doesn't mean you can be careless. So regression equations should be used for predictions only under certain conditions. First of all, the graph of the regression line on the scatter plot needs to confirm that the regression line fits the points reasonably well. Second, your linear correlation coefficient needs to indicate that there is a linear correlation between the two variables. In other words, you've cleared the bar. You've gotten over that threshold of the critical R value so that you can say, yes, we have statistical evidence. There is a sufficiently strong linear correlation here. And third, the prediction cannot extend very much beyond the scope of the available data. Predicting beyond the scope of the data that you have available, because the data is what actually creates the model. The data is what drives the model. So when you go outside the range of the data that you're providing to create the model, you're really going outside the predictive range for the model itself. Now, going just a little bit out of bounds may be okay, but if you go too far out of bounds, it could result in some very bad predictions because you don't really know what your model is going to do beyond the data that you're using to feed it. This act of taking data that's beyond the scope of the available data and using it to make predictions is what we call extrapolation. And again, if you're just a little bit outside the range, it may be okay, but stray too far and you're going to be out there, you're probably going to end up making a bad prediction. Something that'll be totally wrong. Fourth, the linear regression equation is the best model for your sample data. Sometimes you can have a linear regression equation and it's not going to be, even though you can make the equation, it doesn't mean it's the best model for making predictions of your data. So, you got to make sure that the linear regression model is your best source for making predictions before you make predictions with it. If your regression equation does not appear to be a good model, in other words, is useful for making predictions, then the best predicted value is going to be the sample mean. So predictions coming out of your equation, the y hat, that's going to be y bar. Let's look at an example, again, involving shoe print length and height. We're familiar with this data set because we've been examining it for the past several mini lectures. So we have several witnesses who saw a thief steal a man's wallet at a local beach, but their descriptions of the thief's height are varying considerably. So police come out, they measure the length of a shoe print that they find there in the sand, and it's 28 centimeters in length. The question is, what is the best estimate of the thief's height? Second, suppose the shoe print measured 35 centimeters in length. What then would be the best estimate of the thief's height? And third, suppose we did not have the last 5 data points for our regression analysis. What then would be the best estimate of the thief's height for a shoe print length of 28 centimeters? Let's tackle these questions one at a time. First, what is the best estimate of the thief's height if the shoe print length measures 28 centimeters? The model that you create is only as good as the data you use to create it. Garbage in means garbage out. So where does 28 centimeters lie with respect to the range of shoe length values? So imagine a number line where we've got the minimum value from our data set and the maximum value for our data set. So these are minimum and max X values that are feeding the model. 28 centimeters lies on this number line right about here. So we're inside the range of data used to create the model. This is very good. This is typically what you want to see. So it's probably okay to use the regression model given that the value that we want to use for predictions is inside the range of data used to create the model. Now we check our given value, so we're going to substitute in our regression equation, find our best predicted value. So the height is equal to this expression that you see here. We substitute in 28 for the shoe print length, and out comes 174.662. This is the predicted height of our thief. Could round that to 1 decimal point, 174.6. Now, what if the shoe print length measured 35 centimeters? What would be the best estimate for the thief's height now? So we're going to go through the same process. Where does the 35 centimeters that we want to use for a prediction lie with respect to our data? Well, again, bring back the number line. We've got a minimum and a maximum X value. Where does 35 lie on the number line? Well, it's out here a ways. And that means because we're outside the range for the data that's used to create the model, we probably shouldn't use the model to create a prediction. So our best estimate of a predicted value is not going to come from the model. It's going to come from the Y values themselves that we use to create the model. We're just going to take the mean value, and the mean value is going to be our best predictor, because the model we have is not really good for making predictions outside of the range of values used to create it. So we just take the mean value for the height. So we look at our data, look at all the Y values, take the average, which is the mean, and that's 177.22, or rounded to 1 decimal place, 177.2. Third question, suppose we did not have the last 5 data points for our regression model. What then would be the best estimate for the thief's height for a shoe print length of 28 centimeters? So in that case, we've only got the first 5 of our 10 data points, so we're going to need to make a new model. So here's our regression analysis from StatCrunch. And notice the regression equation has some different values in it. So we have a new linear correlation coefficient. We have a new critical R value because now we've got a different sample size. So here's our critical R value table. Assuming we have a 5% significance level, our critical value is 0.878. Notice we don't clear the bar. So our variables are not linearly correlated. That means we should not be using the model to make predictions from the data set. And that means the best predictor is going to be the mean value. So we take the mean value for the 5 data points that are there in our data set, the Y values of those data points, and that's going to give us 177.2. Again, 177.2 is rounded to 1 decimal place. That's going to be our best estimate. So if the model is okay to use the model. If the model is not okay to use, your best estimate is going to be the mean value of your Y variable. That brings us to the end of this mini lecture. I hope you found it helpful. You can find more mini lectures for this and other courses at AspireMountainAcademy.com. Thanks for watching. I'll see you in the next video.